Remember, there are no right or wrong answers. It's all about discussion, right? Collective wisdom is what I'm looking for here. And when I answer, sometimes, believe it or not, I do screw up too. I make a lot of mistakes, but it's okay. That is part of the learning, right? So don't be shy. When I ask a question, say it. Anyone? Okay. Anyone wants to go? Bolishetti, PSCMR, JNTUV, Raju, that is Raju. ABR College. Welcome ABR College. Welcome ABR College. Am I seeing you for the first time? Aditya, I know you are a very active participant. SVCW are active too all the time. Okay, I'm seeing an image of SVCW. కొంచెం ఫోకస్ చేయండి స్టూడెంట్స్ మీద కెమెరా కరెక్ట్గా. The students, do you understand the question that I'm asking you? Raise your hands if you understand the question. I can't quite see the picture well, but try to raise your hands more, that way I can see. Okay, I can't see you properly. Okay, so I will not waste time on that. So obviously, right? Yes, in theory, we should always do theoretical analysis. Imagine, let's assume in this case, let's continue the same case, right? Imagine the linear search is implemented on a faster machine. Pretend that, remember we talked about computing environment, storage and all that. Imagine linear search is implemented on a faster machine and the binary search is implemented on a slower machine. Okay. Now, if the data is small enough, let's say it only has 100 elements. If the data is small enough, if you count the time it takes in the linear search on the faster machine, that will have a better time than the time it takes to do the binary search on a slower machine. Fair enough? Conceptually easy, common sense, right? Yes, in general, binary search is faster than linear search. Our analysis says that. But for the same data, which is not too many elements, let's say 100. I'm just giving you 100 as an example. Obviously, the linear search in a faster machine would give you because it's a fast machine, right? It will execute it fast. And since the binary search is being done on a slower machine, it will be slower. But at some point in time, as your input size increases, okay? Let's say you have a million records now, not 100. A million records. Why even million? Even 10,000 records. As opposed to 100 numbers, you have 10,000 numbers. In that case, even this binary search on a slower machine, that is going to give you better response times than the linear search on the faster machine. So when we are doing these algorithmic analysis, big O notation and all that, we are assuming substantial input sizes. See, it's like programming in the small versus programming in the large. When you learned your first computer science class or programming class, your faculty member would have told you what is the difference between programming in the small and programming in the large. If you write a small 1-page code or a 2-page code, that is programming in the small. Okay? Typically, you don't really apply any big formal analysis to solve the problem. You just sit there at the computer, you hack the code. But programming in the small is not going to work for you when you're, let's say, I ask you to build a complete online registration system so that way students can go enroll in classes online. You cannot sit at a terminal and start coding. It doesn't work like that. Okay? However, software engineering theory, when we talk about theory, what do we say? You should always have a formal process to solving a problem. We say, oh, you need to do requirements gathering. You need to analyze them. You need to communicate with the stakeholder. Then you get into a logical architecture. Then you design your database. Then you design your front end, back end. See that process, right? Theory is one thing. Theory always says follow full process. But when it is very small task, you don't need to apply formalism. So that is why you should always, when you're studying algorithms, right? Yes, this theory provides you the foundation, but when you're a real life programmer, when you're going and working in the industry, if mine is a toy problem to solve, which you can solve in 2 days, don't go deep into all this big algorithm analysis and all that, because my data set is very small. Okay. But when you're working on big projects, this type of analysis will be helpful. Okay. It says what is the average case of linear search in an array of n items if an item is present? Somebody can put the answer in the. You're right, not always. Correct. Whatever you said, SVCW, SET, you're absolutely right. Somebody can put an answer for me in the chat. I actually don't know. Let me say that. I don't know. What is the average case? Is the average case really n squared? It is, right? Looks like it, right? Because n times n plus 1 by 2. That is the average case. You have an n squared number there. It looks like B is the right answer for that. You can convince yourself by Googling, okay? Okay. Let me go to the next slide. Okay. So now we said that searching in a sorted list is faster because that is where we are applying the principle of divide and conquer, right? That's exactly what we are doing. We start at the middle. If that is the item, we got it. If not, we go to the left side or the right side. So pictorially, this is how it looks like. Okay. So you have a low, middle, high. Okay. So is middle item what we are looking for? If not, is it more or less than the targeted item? So we are assuming lower here. So what did we do in the second part of the slide here? We basically now took that middle item that became our high item. Now you do a low. Low is still here. You do divide between low and high. You get the middle item. So you continue to do that. Okay, everyone understand that? Easy? I see DMSSVHC people. Do you understand this picture? Show of hands. Raise your hands. I see all the students in the video. Raise your hands big, high. There you go. Now keep your hands high. Don't bring them down. Keep them high. Because I'm going to ask you one more question. Keep them high. The one in the black shirt or blue who raised the hand, he kept it down. Keep them high again one more time for me, please. Raise your hands again one more time. All of you, whoever understood that, right? Now you tell me, can you write an algorithm for that? How many of you can raise a hand and say they can write an algorithm for that? How many of you can write? Same group of students. Did even one of you raise the hand or not? See, I'm an old man. I can't see unless you raise it big. Okay. Nobody is raising the hand. They're not confident. But you know what? By end of this, one person raised the hand. That's good. Others, don't be shy. Okay. My intention is by end of the term, you will all feel confident that you will all raise your hands. Okay. That is what I want to achieve with all of you. Okay. That's okay. We will go down. So ఇక్కడ algorithm చూద్దాం. Okay. So here is the binary search in action, right? So you have some numbers. It's an array of what, 16. Okay. So this is not it's a complete program. Forget algorithm. I'm just showing you a program. Okay. So you have, what do you have here? Same thing. By now you know that when you're searching, you're taking the list of whatever that list is provided, and then you have a target. And that is a key value. You see how we initialize the variables here. Result equal to -1. Low is 0 because the array index starts with 0. High is list.length -1. Because when you do list.length, what is the length of this one? Length, it gives you a 16, right? And why do we do -1? Because in our computer science, the numbers start from 0. That's why list.length -1 is what you need to do. The rookie mistake that we do, we'll eliminate when we write the program first time, we'll simply call it as list.length. Then you'll get some errors, then you'll fix them, then you figure out that it's always list.length -1. Now you need to get mid because you need to keep track of midpoint, right? Can somebody tell me why you need to keep track of midpoint? The answer is right there, right? Because the midpoint keeps high, either high or low gets that value after you do the first search. So what does this loop say? While result equal to -1, meaning we did not change it, right? Because ultimately result is where we capture. And low is less than or equal to high because you are moving this pointer low towards high. Okay? Low is less than or equal to high. Then mid is nothing but low. Low is 0. High is what was the high, Andy? High was list.length -1. So that is 15. 15 minus 0 divided by 2. Okay? 15 minus 0 divided by 2 is 7.5. No. Am I saying it right? Correct. Low is 0. 0 plus 7.5, 7.5. Now this is integer division, right? Now in integer division, when you do this, is it 7.5 or 7? What does it take, Andy? Can some faculty member put that? What is not visible? My slide deck? Can you see my slide deck or not? Yeah, Jntuk Kakinada is seeing. I hope SVCW. Somebody said they could not see, so I'm just going to 1 second. Okay, hopefully SVCW is seeing my slide now. Do I need to zoom, make it bigger like that? Okay, I just did. Okay, so I think it goes to mid equal to 7, right? I thought I just did. You see it better now? Okay. The reason sometimes I go back to the slide mode is if I enlarge it, put it in presentation mode, I cannot type stuff into the slide. So I play with both the views like that. Whenever I need to write something, I go back to point something. Okay, so now you see mid. So you say if list of mid equal to target, then mid is the point where you have to, that is where you found your target, right? So result gets mid. Okay, else if list of mid is less than target, right? Then low becomes mid plus 1. That means you take the right half. So you move the low to right half of the right side of the mid, right? Now, if that condition is not true, then you move the high pointer to left of that one. Okay. So if I were to see this one in action here, okay. Let's say if the mid is, let's say 17, right? Let's say I'm looking for the value 7 for the sake of argument. Okay. So if I do low plus high, low is 0, 15, 7.5, integer division, we take integer 7. So we are going to be at 7. Okay. So I'm going to compare if list of mid, that is 19, right? Is 19 equal to target? No, because my target is 7. So then what do? I say if list of mid is less than target. List of mid is 19. Is it less than target? No, it is not. So then that means I have to move the high to mid minus 1. So my high was 15, if you see from the fourth line there. So now I move to mid minus 1. That means 7 minus 1, 6. So that means my high would be pointing to this array index 6. You understand that? Yes. Pretty straightforward, right? Okay. Now, 2-minute break. Okay. Break is not free break. It's an exercise break. I'll tell you what I mean by that. Okay. Faculty members, please mentor your students there for the next, let's say 4-5 minutes. Okay. I want the students to trace for key value equal to 3 and key value equal to 30. They can write it on a piece of paper. How many times the low, mid, we can trace it like the following, okay? So how do you trace the algorithm? You start off row 1. Let me create, I only have 10% remaining in my battery. So while you're doing it, I'll go to my room and get the battery, okay? My child's room rather, upstairs. I'll go get the power cord and connect it. What I want you to trace is something like this. Insert table. I think something like this, right? Iteration 1. Chala green, chala ugly on this. So let me see if I can select some better color. Filler. Okay, let me see if I go to home. I go to filler. I'll remove the filler. Wow, it didn't change. What happened? That was a filler color. Hold on, bear with me for a second. Okay, let me do it one more time. Okay, I'll live with green for now. Home. So I'll say iteration. Okay, I'll choose font black. Iteration 1. Okay, what low? Let me make all this black. What is the low? What is the high? Sorry, I can't spell. What is the mid? What is the result? Okay. So trace for key value 3 and how many iterations, right? Iteration 1, 2, 3, 4 like that, right? So I'll copy paste this one into this one. Okay, that is the code. And then ikkada for convenience, I'm going to put the table here. Okay. Oh, Control Z. How come the table did not come? 1 second. Control C. Control V. 1 second, Andy. I'm trying to manipulate.
we need to do a quick revision of this class in the beginning of next class. I don't know what you mean by revision, but we'll definitely review that. No problem. Every class we review what we did in the last class, right? I'm assuming that's what you meant there. Okay. So let me ask Pragati again, since a wonderful student there did not hear me. How many of you were able to follow those steps and come up with the answers? Three iterations for 3, and I think for 31, 4 iterations. Are you raising your hand there? Were you able to come up with the solution there? Okay, I see kind of 1 or 2 tentative. Okay. But these are the kind of things. There is no other choice but to learn this stuff, right? Okay. And what is the worst case big O for this? Did anyone put that in the chat there? Worst case, even if you compute, it's basically log of n, right? Because remember, it's actually, remember the binaries, you're always dividing it by half. So it's basically, you saw from answers also that you got, it's basically of the order of log n. Okay, you get a lot more practice on these things. So if you're feeling a little bit nervous, don't be shy. Okay, I have a lot of slides like this to show you, so that way you can become better in these things. So here is the same thing, slightly slight change here. This is the standard but generic binary search algorithm. Okay, there's a reason why I put this slide here. It's the same thing as what you have seen before, right? There is no change there. Okay, slight changes, but it's still not that big. Okay, result -1, low less than or equal to high. We had the same if then else statements. We had the same mid statement. Everything looks same. For those of you who are wondering what this notation is, in Java, what happens is, or in C++, the thing that comes before the dot is called the object, and then the thing that comes after the dot is called the method. So think of it as a method. Okay, I know that you have not learned full Java programming language or C++ for that matter, but as long as you see that, hey, if you know what the function that it is doing, it's pretty easy to read this code, right? Okay, this is the generic one. But look what happens here. All of a sudden I'm introducing recursion. Remember when I showed you in the Word document, let me share my Word document here again. In the Word document, when we talked about this one, remember we said this thing called recursion. Okay, so I'm assuming you probably learned what recursion is in your programming language. If not, here is your chance to look at it. Okay, the same algorithm, the same code, not your algorithm, has been written using the quantum of recursion. What does recursion mean? Let's look at it here. Okay, still the same thing here. You have the binary search. You get the list. You are looking at the target. Couple of more extra parameters here. What is the first and the last? So you know the bounds, if you will, right? So you go to the if statement here, and integer mid, low plus high minus low divided by 2. It is the same concept as before, right? And then if you find it in the middle, you return mid. That's the same concept again. Okay? Else, if list of mid is greater than target, that means now you need to take the right side of it. Now what is he doing here? Instead of, he is now calling the same function again. That's what recursion is. You are calling the same function again. Now your first is the low and mid -1 is the high, right? So you can see now you change the value of what that high is to mid -1, and then you're calling that function again. Okay, so recursion, somehow you have a baseline case We'll do it formally again, but this is just to give you, think of it as like an appetizer for that, right? That is what I'm giving you here, introducing you to recursion. So while you're going through that loop, all you're doing is calling the same function again. That is the concept behind recursion. When you do n factorial, you know how to compute factorials, right? What is like 2 factorial? 2 factorial is 2. 3 factorial is 3 times 2 times 1, right? 6. If you write it down on a piece of paper, you see you're basically calling the same function again, right? If I do 3 factorial, what I'm doing is I'm taking 3 times 2 factorial. So I'm using the same factorial function. That is a classic example of recursion. We kind of also use it for Fibonacci sequence. Okay, we'll do it formally, but this is just an introduction for you. Okay, let me make sure I have your chat open and participant list open. Okay. Questions, comments before I move on? Okay. Let me put it in presentation mode now. Okay. Now, is that the only search algorithm? No. There are many search algorithms here. Okay. There's something called interpolation search. Okay. Index searching. We use hash tables. We use binary search trees. Okay. I have no clue what Grover's algorithm is. Okay. If any faculty member studied Grover's algorithm, please feel free to put it in the community. I didn't get time to look up what Grover's algorithm is before I came to this class today. Okay. Best first. Okay. Different types of algorithms. It's like I would call it like a black hole. There are so many different types of search algorithms, and people get PhDs doing these things. One of the famous professors who taught me graph theory is well known in these things. Graph theory and all is used for search, right? Google uses that. So I learned some of these things from him. Interesting, right? Let's talk about sorting. Okay, very classic case, right? Here are some examples of sorting, right? Everything we sort in life, whatever we do, even for example, when I get up in the morning, I have a daily to-do list, right? I'll say, okay, today is Sunday. I have to, for example, my list was I had to pick up my daughter and wife from all the way in Irvine. Okay? Then drive to Santa Barbara to meet my other daughter for lunch. Then I had to come and help my kid move his stuff to his apartment. Then do the class. Different things. I list them down. Then I sort them because there's an order in which I have to do those things. So sorting is everywhere. Okay? What is the most famous sort? Bubble sort, right? Everyone knows what bubble sort is. So let's look at bubble sort. Okay? So why do we sort? To make searching for data faster. Okay? So you can see with respect to sorting, right? When you work with a fixed size storage container, then it's going to be very expensive to expand it. Let's say you declare a 20 element array to store the list of students in your class. Now, all of a sudden, the class size now is, they've added 5 more students, and you can't store them in the 20 element array. Now you have to expand that array, and then again put all the 25 members in a sorted form. Okay? Now, famous sorts are bubble sort, selection sort, and insertion sort. Let's look at what bubble sort is, right? One more time. I think there's one more slide here before I do that. Okay? So you can see there are some properties of sorts. Okay? Some of these things, by the way, I even forgot. I did that long time ago. If you see the second bullet, it says if a sort guarantees the relative order of equal items stays the same, then it's called a stable sort. You can see here the 7 occurs multiple times, but those locations don't change. They are there. Okay? The one at subscription 1, this is a subscription 1 meaning is assuming the author is assuming here array starts at 1. Okay? Or actually, yeah, 7 1 first time occurrence, 7 2 second time occurrence, 7 3 third time occurrence. As long as your sort algorithm guarantees that they don't change, they are there, it's called a stable sort. Okay? Now, when you apply some algorithm to sort those things, you can see how those 7 1 7 2 7 3 they still occur in the same order. Okay? Apparently, sorting a table in Wikipedia by one criteria, then another by country, then by major wins. If you look at Wikipedia, that's where these things are used. It's used everywhere, not just Wikipedia, right? Okay. So what does a bubble sort do? Tell me, I did not show you the bubble sort code here, but we talked about bubble sort last time, right? Can someone remember what happens in bubble sort after iteration 1? Just out of the blue, I'm asking a question. So you are given a set of random numbers. I'm saying apply bubble sort. Faculty members, please feel free to help me out there. What happens after iteration 1 in bubble sort? Which element would be in the right place? Let me put it that way. Which element at the end of iteration 1 would be in the right place when you are sorting an array of numbers? By the way, please feel free. If you don't remember, you can say, I don't remember. And that is perfectly legitimate. The amount of knowledge that is there is so vast, sometimes hard to remember. If I remember right, in bubble sort, after the end of iteration 1, I think the highest element in ascending order, I'm assuming ascending order, okay? The highest element will be in its right location. Okay? If I remember right, okay? If somebody wants to verify that and either say what I said is right or wrong, please feel free to do so. Okay? But here this slide we are talking about selection sort. Okay, what does selection sort do? Look at the top thing here, right? Search to the left and find the smallest element. Okay? So we are always looking for the smallest element and swapping the smallest element with the first element. Okay? So we are going from smallest to the highest here. Okay? So you are given an array of n numbers. You look at the lowest number there, okay, and then put it in the first place. Okay? We'll come to the code in a minute. After you put it in the first place, then what happens? That place is taken, right? Now you have to go to the next element. So you put the lowest element in A0, then you move your index to A1. Now you look again for the smallest element in the remaining, and then you put that in A1, and like that you continue to do. So that is what this algorithm is showing there. Okay? Integer I, list.length minus 1. Remember, list.length minus 1 always. Minimum equal to I, meaning you are saying, hey, my minimum index, the lowest is I for now. So I get 0 to begin with. Now you say for integer j equal to I plus 1, because we are now looking for first element A1, A2, A3, and so on, up to the end of the array. Now you do the comparison. That's what you're doing here, right? When you do this comparison, sorry, I have to put it in slide mode here. Assuming you can see that. You can see here you're doing the comparison here. Depending on what the comparison is, minimum gets j. Because at the end of the loop, what would j contain? J contains the lowest element, right? So you're going to swap it. You're going to put that in the very first, or wherever the pointer is pointing the low end. You put that smallest element there, and then you continue with the rest of the array. See how easy it is, right? In one sense, once you write what the concept of the algorithm is, right? You write this code. Now, will you get the code right the first time? Is there anyone who can write the code first time here? Even when I show the code. The chances are no. No one writes the code right the first time unless he's a super genius, okay? You start writing code, then you compile, hopefully you'll remove the syntax errors, then you run, you give some test data, you see whether the test data has come out right or wrong. If it has not come out right, then what do? You put breakpoints in your code. Then you see where the code is breaking. Then you fix that code. That is how you develop these things. Okay? Okay, I hear a whole bunch of silence. Let me pause here. Questions, comments? Is there anyone who does not understand the principle behind selection sort? Okay, Raju said they put S there. I don't know what S means there. They're trying to type YES or just they typed S. Cannot understand what S means. You can help me out there. Okay, so you understand selection sort. See, I need feedback. Students, ask your faculty members to type stuff. Hey, we understand, or slow down, explain it again. You have to give me feedback, then I can continue, right? Otherwise, I assume you understood, then we move fast. Okay? Unless I get feedback, I would not be able to help you. Okay, here is the selection sort. Okay? So how many iterations would happen for selection sort? You don't have to, if you don't have the answer, you don't have to answer it right away. But think about it. Think about, let us say, take about a 4 element. Let's say, how would I do that, right? Whenever I'm learning, I'm not big on a theory thing, by the way. I first need examples to generalize to a theory, right? So what I typically do, I take like rule of thumb, I apply 7 plus or minus 2. There's a cognitive psychology rule called 7 plus or minus 2 rule. As an aside, what it means is a human being can remember 7 plus or minus 2 things at any given time. Say 15 names to you and ask you to recall, chances are all of you will recall about 7 plus or minus 2, meaning low end is 5 and high end is 9. That many names you can recall. Now that rule is applied to all branches of computer science. Okay, wherever you go, 7 plus or minus 2. How do I apply that in practice here? For the relevant example, I say, in order for me to understand the big O, I can take 7 plus or minus 2 elements here. Let's say I take 5. I apply the selection sort principle that I have given you in the previous slide. See how many iterations it's going to take. Okay, then maybe I'll take 9 and do that. That gives me some idea. It's kind of like almost like proof by induction, right? That's what I'm doing here. So think about it. See what the big O is for you. Okay? Generic. Okay. Now, there's a question here called, is selection sort always stable? I don't know the answer. I'm being very honest with you. So what does stable mean? What is the definition of stable that we gave? We said if there are 2 numbers which are same numbers, I mean, just like remember the example of 7 that I gave you, would those numbers also be swapped or they would retain their respective positions? That is what stability is, right? That's how we define. Check it out. This is where I say that don't rely on what my answer is. You give those 5 numbers, make 5 or 7 numbers, make 2 of them the same numbers and see if your algorithm swaps them or keeps them in their respective positions. If it keeps them in their respective positions, then it's a stable. Selection sort is stable. If not, it is not stable. As simple as that. Okay? No need to remember, right? After you do it a few times, you'll know, yes, it is stable or it is not stable, whatever the answer is. Okay. Now you have another thing called insertion sort. Okay. So what is insertion sort? By the way, after teaching the class, if you ask me tomorrow or the day after, can you tell me what insertion sort is? Very difficult for me to tell you, because I don't believe in memorizing these sorts. But if your exams in India dictate that you need to know these things by heart, you need to memorize them. Okay? The way I memorize it, I write programs quite a bit. That's how I memorize it. Typically, I say, okay, I understand the general principles. If I need to know what sort to use, I'll go look up what that sort algorithm is and implement it, right? No need to memorize this stuff. Just understand the concepts, in my opinion. But I'll look up to your faculty members to guide you. Hey, you need to memorize this, then you do. Okay? Okay. So Raju, JNTUV, Raju is JNTUV. So I asked a question in the chat earlier saying the highest element will be in its right location. I asked them to verify whether it is correct answer or wrong answer. They said no. You meant no for that question, I'm assuming. If that is no, then you can put the right answer also, what the right answer is. Okay? Okay. So what does insertion sort do here? The first item is sorted. Compare the second item to the first item. Okay? Then you smaller swap. Okay? Then you're taking third item. Compare to item next to it. Need to swap, then swap. So what he is doing is, he is comparing, in insertion sort, you're comparing adjacent elements. And then you're swapping them based on which one is lower. Okay? If it is smaller, you swap. Otherwise, you move on. So that is how you do that. Okay? Now, students might have a question, why there are so many different types of sorting algorithm? Did it ever occur to you why there are so many different types of sorting algorithm? Can somebody answer why we have so many? That's a legitimate question. Huh? It's a legitimate exam question. Okay, why we have so many sorting algorithms? Okay. If I were to get that question in my exam, what would be my answer? My answer would be these people have nothing better to do, right? That's why they invented so many. But on a more serious note, the reason why you have different types is there are different ideas, and there are so many permutations and combinations of solutions. If you take chess, for example, right? How many permutations and combinations are there of the moves? Anything, it's like infinite variations, right? I mean, there is some limit, but for purpose of normal human, you could say infinite. So people are always looking for optimizing. So any of these things, when these things have been proposed, the way it works in research is somebody writes an algorithm. Somebody else says, oh, for this particular data set that I have, if I tweak the algorithm a little bit more, I get better results. Then I publish that new algorithm. Okay? That is how these algorithms have come about. Even though it's sorting, they're the most famous sort. Faculty, it's a brain teaser for faculty members too. What is the most famous sort of all? Other than bubble sort. Everyone knows bubble sort, right? As computer scientists, we all know bubble sort. The most famous sort of all. I'm putting it in chat here. Quick sort. Okay? And I'm keeping track of time, but bear with me. Quick sort. Who invented quick sort? Anyone remembers the author's name? I will send them a coupon, lunch coupons for them. Dinner for two. If it's a faculty member is answering, faculty member and their spouse, you get dinner for two from me. If you type the name of the person who invented quick sort. The only person who cannot answer is Chakravarti. Chakravarti is not allowed to answer because he knows all the answers. No one knows the name? Okay. Check him out. I put the name there, Tony Hoare. Okay. So Tony Hoare is a very famous professor. Okay. And then he became famous according to Dijkstra. Dijkstra is another famous man, right? We all know Dijkstra. I share these kinds of stories in my class, so you have to bear with me. Who is Dijkstra? Dijkstra is the founding father of computer science. He was the first guy who gave multi-user operating systems, right? Multics, in MIT, I think, long time ago. MIT or somewhere else. He was the guy who gave us operating systems concepts of semaphores. He was the guy who said you should not use go-to statement in programming languages. You name any aspect, any branch of computer science, he created the foundation for us. So once I was attending a lecture where Tony Hoare was invited to give the lecture and Dijkstra was introducing him to us. Big man, right? These are like, when I see them, the goosebumps, in their presence, you feel that. Then he was telling us, he said, Tony Hoare is very lucky. He became world famous just because of his quicksort algorithm. Other than that, he did not do anything else. Not true, but somewhat true, right? So, anyway, going back to this. So this is insertion sort. I gave you a piece of code. Now, I don't want to go through each and every line of code, right? How the insertion sort works. What I expect students is when I show these things, I expect them to run through this algorithm, take some test data, run through them on a piece of paper. You don't need to write code. Just take some numbers, run through it. We just showed you what selection sort, insertion sort, and bubble sort I already showed you last time. Okay? And some of you actually even wrote that in our community. Run through them, see how it works. Then, if you want to do one better than that, go write this in the programming language class that you're taking right now. Right? I believe you're taking some programming language class right now, correct? Go implement this in that language. That is how you assimilate the concepts. Okay? Not just listening to my lecture for 2 hours. Okay. Now again, I cannot impose those things. One thought was I was supposed to teach that programming class too, so that way I can actually make you implement them. But since I'm not teaching that, it's an optional thing. Okay. Okay. So here is where I think we can stop today. Is this one? Let's see what comes next. Okay. The question for you, food for thought for you, where I want you to go and put it in the discussion forum. I'm going to create a topic called comparing algorithms, and I'll put this question. Which algorithm do you think will be faster given random data? Selection sort or insertion sort? Okay. And I'm going to put that in the community forum for you. Okay. Everyone understands that? Okay. Now, obviously, you can always do a Google search and get answers. Okay. Thanks to the internet technology now, you can get answers on the internet. The idea here is, right, some kind of a honor system here. Okay, honor system means you can generate random data, by the way. You know that, right? In a computer programming class that you take, you can generate random data. And then you can even write this algorithm if you are interested in your language. Check it out, which is giving you good times. You know how you can put the start time and end time, right, in your programming? If you have not used start time and end time, you can use that code. You can see a start time function, an end time function, put it there, check out your times. See if your experimental values would coincide with what the internet says when you search for an answer for this. Okay? Fair enough? That's your food for thought for the day. Okay, I'll be here for some more time. I'll be happy to answer questions and comments. I'll be here. So I'm about to post this slide deck there for you to review. Chakravarti garu, are you still there or you are in a meeting somewhere? Some administrative details. We have a faculty. Chappandi Chakravarti garu. Excellent. మీరు రివిజన్ అన్నారా రివ్యూ అన్నారా మీరు ఏమన్నారో నాకు అర్థం అవ్వలేదు. తప్పకుండా అండి తప్పకుండా విల్ రివ్యూ డెఫినెట్లీ. అండ్ మై అపాలజీస్ ఫర్ ది delay again. As I told you, I have to drive 400 miles from Southern California to Northern California. Then bring my son here, who is starting a job tomorrow morning. And now after the class, I have to go and assemble his bed in his apartment for the next 2 hours. Okay. So, and then internet connection is spotty. So am I on video right now? Do you see my video? Let me stop. Do you see my video only? You can see I'm actually sitting in a sports court here with some pool table and all that here. The lady, because I had to come down, internet was not coming in the apartment. I had to come down, sit in the lobby and do it. And then the reception, there's a 24-hour concierge, said, sports court is now not available for anyone else. I'll open it for you. So she made me sit here and do the class. So I go to extreme lengths to do my classes. So apologies again, but I hope you had fun. You learned that we went deep. If students are feeling, oh my God, if this is already deep, then what else is coming? Don't be scared. This is all fun. As long as you have fun, right, you will learn. Okay, and then we'll review. And by now you know already, I continue the same concepts over and over again. We did arrays already last few classes, but if you notice something, in my style of teaching, what I do, I keep adding layers to the same thing, slowly. That's how the students will learn. I'll leave you with one last thought. I learned it from my brother-in-law a long time ago. He said, if somebody has to become an expert in some subject matter, they have to do it 22 times, they have to review the material. Obviously, we don't have time for 22 times. At least three times, 4 times, I review that in different ways. Okay, I'm done with the class, but I'll be here for some more time if you have questions. And Tuesday, we are on, right? So together with the faculty meeting? Okay. My class is not that day, you know that, right? Okay. 9:30 to 10:30. So do you want to send a reminder to the rest of the faculty in an email? So that way they will all log in, okay? Thank you. And you still owe me the faculty members list. If you can send that to me, I will send them a note before the meeting. Okay. Thanks, Andy. Good night. And have a good, actually for you, it's good morning, right? Have a wonderful day, everyone. Okay, bye.